Okay, so what we're going to look at today are Taylor polynomials. Do you remember when we did approximations using tangent lines? Linear. Now we're going to use an approximation that's not a line. It'll be a quadratic or a cubic or something with a higher power. So it's the same idea as using a tangent line approximation, but the approximation is better. Does this make sense? Okay, so I'm going to share my screen and show you some of these because they're very cool. So here is sine. Let me bring up sine. Oops. Sorry, there's a lot going on here. All right, so there is, a linear approximation. So now I'm going to slide it and make the power higher. So look at what happens. Do you see how it's like a very good approximation of it? And what we're going to look at, not today, but eventually, is if you take this series out to infinity, what you get is the actual function. So you can represent functions as what are called power series. You take this out forever, but look at that, isn't that neat? Okay, so let's get rid of that one. I'll show you another one. Bless you. Cosine looks a lot the same. Here, you know what? I'll just show you cosine. It's not a big deal. So there's cosine. You turn this on. So that's a quadratic. And then let me make the power go higher here. You can go when you finish your quiz and turn it in. So look, as I raise the power higher, do you see what's going on? How it's like becoming the actual function? It is cool. And let me turn that one off. And then here's e to the x. All right, and then as I raise the power, so there's a tangent line, and then there's a quadratic, cubic, quartic to the fourth power, and then this looks kind of cool. What happens at the end is it just keeps on. I can't make it go any further, but it would eventually become the function. Does this make sense? Cool, this stuff is cool, guys. It's really cool. All right, so you can read through that. Oh, wait, question, go ahead. It's sometimes if getting the derivative would be needlessly complicated, or again, sometimes they don't give you all that information. Do you remember the table problems that we did when we were doing the derivative rules, where you didn't actually have a function? All they would give you is a table, x, f of x, f prime, that's all they give you because they want you to be able to analyze it. So they would kind of not give you all of that information. But again, the idea is you're writing a polynomial that's an approximation. Instead of something linear, it's going to be a polynomial. So you can read through all of that. Again, we're short in time, so I'm going to kind of keep thinking, bless you. So a Taylor polynomial, and n would be the power. So it'll say write a polynomial with power 3 or power 4 or power whatever it is. So it's f of whatever the number it's centered at. We say it's centered at c. So say it was centered at 2, you'd have f of 2 over 0 factorial x minus c to the nothing. And then this is the first derivative over 1 factorial, and then it's to the first power. Second derivative over 2 factorial, and it's to the second power. Do you guys see what's going on here? Then it would be the third derivative over 3 factorial, and then to the third power. Now, if it's centered at 0, that's like a special one. If it's centered at 0, it's called a Maclaurin polynomial. So that's a Taylor polynomial that's centered at 0. Is what's going on there. Okay, so for e to the x, find the second degree Maclaurin polynomial. That means it's going to be centered at 0. I write this out every single time, and here's my pep talk for this. This really does not have much to do with intelligence. It's not really about being smart. It's about staying organized. Do you know what I'm saying? I know people that are absolutely brilliant and can't get through this because they aren't organized. My suggestion is write it every time. I know you're going to either take that or leave that, but I would write it every time, all right? P sub 2 of x, because it says a second degree, we want n to be 2. And this one's going to be centered at 0 because it says Maclaurin. So it's going to be f of 0 over 0 factorial x to the 0. plus, then you're going to do the first derivative at 0 over 1 factorial x to the 1. See, it's like pattern building. And then the second derivative at 0 over 2 factorial x to the second. And then we can stop there because it just said second degree. Now you need all of those derivatives. What's the really awesome thing about e to the x? The first derivative is e to the x, the second derivative is e to the x, the third derivative is e to the x. We use e to the x a lot for these because it makes life easy, okay? So this is going to be e to the 0. What would that be? 1. 0 factorial is also 1, and anything to the 0 power is 1. So this entire first thing is just 1. Plus, right, first derivative is e to the x, e to the 0 is 1, over 1 factorial, which is 1, x to the first, so 1x. Plus, second derivative is e to the x. E to the 0, 1, over 2 factorial, that would be 2, so 1/2 x squared, and that is your polynomial. That's your second degree polynomial. Again, what we're going to look at later is an infinite number of terms, because then that would become the function itself if you take it out infinitely. This is making sense? Like, it's almost like, do you remember how last unit we did partial sums? And then there was the true sum if you added to infinity. It's like this is a partial sum. Yeah, well, you want it in this order. You want it in, I know that's kind of weird. You want it in ascending order. You want to start with the nothing and then to the first and then to the second, because it's like the first term, the second, well, I guess that'd be the 0th term, first term, second term. So you want it in that order. This one, I'm actually wondering now why I kind of even stuck this on here, but find the nth degree Maclaurin polynomial. It's exactly what we just did. So you can pretty much recopy that. 1 plus x plus 1/2 x squared. And basically what I'm asking you to do is write out the general term. So it's going to be 1 over n factorial x to the n. And normally I would ask you guys to try and think about that and see like if you could come up with it, but we're on such shortened time today, I'm just telling it to you. But do you guys see that there? This would be 0 factorial, 1 factorial, 2 factorial, and then x to the 0 to the first to the second. Like that's the in general like format for that. All right, again, using e to the x, find the third degree Taylor polynomial centered at 3. We're just going to practice that again. I'm just changing where it's centered and I changed the degree. So it's basically just another practice problem. Again, I write this out every single time. I guess you can skip it, but again, it's about organization. All right, so it is going to be f of 3. So the nothing derivative, which is just the actual function, over 0 factorial x minus 3 to the nothing. And then it would be the first derivative at 3 over 1 factorial x minus 3 to the first. And then it would be the second derivative at 3 over 2 factorial x minus 3 to the second. And then this one's going to have all the 3's in it. Now, once I get past the second derivative, once I get to the third derivative, I'll just put a little 3 there. And that's like generally the notation, you'll see that. So the third derivative at 3 over 3 factorial x minus 3 to the third. All right, f of 3, the function was e to the x. So that would just be e to the third over, this would just be 1. So just e to the third, and then all of that would just be 1. So just e to the third. Plus, right, again, we used e to the x because all the derivatives are the same. This would be e to the third over 1, which is just e to the third, and then x minus 3 to the first. Plus, e to the third over 2, x minus 3 squared, and then e to the third over, what is 3 factorial going to give us? 6, good. And then x minus 3 cubed. Are we getting the hang of it? Okay, go ahead and flip it over. Because I'm going to change the function. Now we're going to look at ln of x. We want the fourth degree Taylor polynomial centered at 1. And then we're going to use it to approximate ln of 1.1, just using the calculator. I have mine handy. I'll just type it in first. Okay. So again, I write this out every single time. You can, like, I guess, choose not to, but I'm telling you, you're going to be upset if you miss something because you weren't organized enough, right? It will be f of 0, or no, not 0. Where are we centered? 1. F of 1 over 0 factorial x minus 1 to the nothing. First derivative at 1 over 1 factorial x minus 1 to the 1. What's the next one going to be? F double prime of 1, good, over 2 factorial x minus 1 squared. Perfect. And then third derivative at 1 over 3 factorial x minus 1 to the third. And then I ran out of room. Wait, it was fourth, right? Fourth derivative at 1 over 4 factorial x minus 1 to the fourth. I'm terribly sorry. You know what? I could have made it fit if there wasn't a hole in the paper. I know you're like, I don't want to write that. You technically don't have to. You can just jump straight to the answer, but I will mark it wrong if you make a mistake. So like you've been warned, right? So p sub 4 of x equals f of 1. All right, ln of 1, 0. That entire first thing is just 0. Plus, all right, now we need the first derivative. I'm just going to write it right above here. What is the first derivative for ln? 1 over x, good. So we are plugging in 1. That would just give us 1 over 1. So that whole thing is 1, and then just x minus 1. All right, now we need the second derivative. I'm just going to write it off to the side here. This would be x to the negative 1. In your mind, think of it that way, x to the negative 1. You would bring the negative down, and then it would drop to a negative 2. So it'll be negative 1 over x squared. And we're plugging in 1, so that would give us negative 1. So this is going to be minus 1 over, you know what, I'm just going to actually leave that as 2 factorial. Because, well, you know what, I guess I'll simplify it down. That would just be 2. 1/2 x minus 2 squared, or x minus 1 squared. Too much going on here today. All right, so now we're on this one. We need the third derivative. Bless you. Thank you. So this is negative 1x to the negative 2. So when you bring the negative 2 down, the negatives will cancel. It'll just be 2. Good. And we're plugging in 1. So that would just be 2 over 3 factorial is 6. 2 6 1/3. X minus 1 cubed. Last one, we need the fourth derivative. This would be 2x to the negative third. So when you bring that down, it'll be negative 6 over x to the fourth. Again, we're plugging in 1. So that would just be negative 6 over 4 factorial is 24. So 6 over 24 will be 1/4. All right, so that's the polynomial, and it said use it to approximate ln of 1.1. So if you plug 1.1 into all of that, you know what, for the sake of time, I already have it written down. I'm just going to tell you what it is. 0.095. If I asked you to plug in your calculator, plugging 1.1 into all of this, could you do it? Like if I made you do that? Okay. Now, say you wanted to do a Maclaurin polynomial instead of a Taylor polynomial. Usually you do, because this would be centered at 0, so it'd be a little bit less work. You would use this as your function instead, and you would just plug in 0.1 instead of 1.1. You're almost just making it like a not almost like a transformation, that's what it is. You see how I'm just shifting it so that we can center it at 0 instead? We're not going to have to redo all this work in case you were worried about that. When you write out the polynomial, it's going to be this exact same thing, except centered at 0. I'm going to skip this term because that's 0. So this would just be x to the first minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the fourth. And if you plug in 0.1 to that, because we're just going to plug in 0.1 instead of 1.1, you will get the exact same thing. So sometimes it's nice if you shift it a little bit so you can do a Maclaurin polynomial instead of a Taylor polynomial, so you don't have to deal with all of this like x minus 1. Do you see what I'm saying? It comes out to the same thing anyway, for what it's worth. All right, for cosine of x, find the 6th degree Maclaurin polynomial. I know you're like, we hate you. If you don't want to write this, you can just watch me. I'm going to write it out though. I know it's to the 6th, but I do it every single time. The one nice thing is that it's Maclaurin, all right? So it'll be f of 0 over 0 factorial x to the nothing. First derivative at 0, 1 factorial x to the first. This like definitely goes in the tedious but not difficult category. I just do that every time. I don't know. Maybe that's me just being. Oh, yes, thank you. There we go. X squared, x to the third, x to the fourth, x to the fifth. Before we get into this, we're going to need all of those derivatives like we did with the ln of x. I just wrote them along the top of the paper. Let's just go ahead and find the derivatives really quick. What is your derivative of cosine? I'm just going to write them along the bottom. Negative sine. And then the second derivative of sine would be cosine, so negative cosine. Third derivative would be sine, positive sine, good. And fourth derivative would be cosine, which puts you right back to the beginning, and it's just going to keep cycling through this, right? So I don't need to write out, I know we need to go to the 6th one, but I don't need to write out anymore. All right, so plugging in 0 to our function, what is cosine of 0? Because it's not 0. 1 over 1, and then this is also 1. So that entire first thing is 1. The first derivative is sine. Now sine of 0 is 0, so that term goes to 0. So now we're on the second derivative. If you plug in 0, cosine of 0 is 1, negative. So negative 1 over 2 factorial x squared. I didn't forget the x squared that time. Third derivative, it's sine. Sine of 0 is 0, so that term's gone. Every other one is going to go away. All right, fourth derivative, cosine of 0 is 1, so it'll be 1 over 4 factorial x to the fourth. What happens to this one? Goes away because it was negative sine. Good, and that is where I was headed with this, is that you could see the pattern. You're probably like, why on earth did she make us go out to the 6th? Because you wouldn't have seen the pattern if I hadn't. If you don't go far enough, because every other one of them disappears. What would the next one be, just for the sake of argument? And then minus, see, if I didn't make you do it that far, you wouldn't have seen the pattern, okay? I have 2 minutes, we can finish this last one. Now this is e to the x times f of x, and I think, Evan, this might kind of answer your question, like, see how they didn't really give us a function, like all you have is this stuff? So e to the x, we just did on this side of the paper. It's 1 plus x plus 1/2 x squared. We just did it right there. F of x, we're going to need to work out. So it'll be 6, which I'm getting from the table right there, over 0 factorial x to the nothing. And then 3 over 1 factorial x to the first. And then minus 2 over 2 factorial x to the second. which let's simplify that down. The entire first term will just be 6. And then this would be 3x. This would cancel, so just minus x squared. So these are the two functions, the e to the x and then the f of x. All you have to do is multiply them together. Here's the thing. It said what degree do we want? Second. So you're going to distribute the 1 to everything. You're going to distribute the x to everything, and you're going to distribute the 1/2 x squared to everything. But if there's a term that goes over a power of 2, you don't include it. Because in theory, these could go out forever and ever, and we're just like not going that far. Does that make sense? Okay. Distributing a 1, that'll give you 6 plus 3x minus x squared. Distributing an x will give you 6x plus 3x squared. And then you would take the x to this one, but you would stop there because why? It goes over 2. And then distribute the 1/2 x squared will give you 3x squared.
Today during the tornado warning.